I think it's recording. Do you get
Yeah, it's all good. Yeah.
awesome? All right. Hey, hello everybody. So I'm Yalan and I'm going to be walking you through what a drand beacon is today. And so first things first, we saw last time how we could access beacons, right? So, but we saw that very briefly. So I figured it wouldn't hurt to see it again. So the easiest way of getting a beacon is to go through the HTTP relays. The HTTP relays are being run by a few partners in the League of Entropy. So here we can see the api.drand.sh relay, which is run by the drand team at Protocol Labs. And there are other relays run by Cloudflare and StoreSwift. And we also have gossip sub relays, which are not using HTTP, but gossip tab instead. And yeah, I'm only demonstrating the HTTP relays today, but basically what you do is you go to api.drand.sh/public/latest, for example, if you want to get the latest round, or you can go to /public/ the number of the round you want, and you will get the drand beacon. And so, as I said, it's a HTTP endpoint, so you can also use your terminal to access it, or you could do it with, I don't know, Python code, Java, JavaScript, whatever languages you want. You just need to access that HTTP endpoint, and it will return a JSON formatted beacon to you. So here we can see it in the terminal using curl and pretty JSON, pretty printer. So if you want to do it in Go, we also have the drand client, which has a HTTP client where you can just instantiate an HTTP client using a given relay's name, and then you can tell it you want to access a specific chain hash, and then you can get beacons like that. Here I'm getting the beacon number 0, which means get the latest one. It's a keyword because there is no beacon 0 since we start at 1. And before that, it's Genesis, and the Genesis is a hard-coded seed. But we'll see that very quickly. So what's a beacon really? So as you can see here, we got a round number, we got a randomness value that is relatively short, we got a signature that is relatively large, and we get a previous signature that's also relatively large. And so let's go back a bit, and recall what drand is. So drand is an open source software made in Go that is meant to be run by a set of servers or nodes. And these servers are going to produce random beacons at a given frequency. So for example, the mainnet has two networks, two chains running. One of them is running at the 30-second frequency. The other chain is running at the 3-second frequency. And drand is meant to produce verifiable public randomness. And the trick here is the keyword verifiable. What does that mean in our case? It means that we are issuing BLS signatures as the League of Entropy that anybody can verify. And if the signature checks out against the public key of the league, then you can be ensured you've got a valid beacon that was actually produced by the League of Entropy. So we're using pairing-based cryptography. That's the BLS signature scheme, and we're instantiating it on the BLS 12381 curve, which is a pairing-friendly curve with roughly 117 bits of security according to the most recent attacks, which is plenty enough. As long as we're above 100 or 110 bits of security, usually we say it's okay. And drand actually binds together different entropy sources. For example, Cloudflare used their lava lamp wall to instantiate their key share during the initial DKG. Kudowski Security used their own in-house Chacha-based PRNG. University of Chile was using the seismic data from Chile as an entropy source. So yeah, you can basically bring your own randomness to the mix during the initial distributed key generation, and that will help the league or the group running the drand distributed key generation produce a secure and safe source of entropy for its key. And once the key is generated, all beacons will be deterministic from that point. And now we'll see a bit more about what the properties we have for beacons. So drand is meant to be decentralized so that there is no single point of failure. Like if a node is down, the rest of the league can still operate because we currently, I think, have a threshold of 13 out of 25 nodes. So it means we could have 12 nodes going down and the league would still be operating as usual without users or without, most people not noticing anything. Then the beacons that we're producing are meant to be unpredictable so that no single party can predict the value of the next beacon or the beacon that will be producing tomorrow or whatsoever. And that is true as long as there is never a threshold amount of nodes in the network that are malicious at once. That's really the key security assumption behind the whole League of Entropy. It's that there is never a threshold amount of nodes that are malicious at the same time, And so the beacons are also bias resistant. That's because the way we produce them ensures that each random value is uniformly distributed on all the possible bit strings we can get. And then it's verifiable because we use aggregated BLS signatures and we can verify them against the public key of the group. So I mentioned BLS 12381, and that's the curve we're using for BLS signatures. That curve is using a pairing with G1 and G2 being the two bilinear arguments of the pairing, and GT being the target group. And the interesting bit here is that G1 is relatively small with 48 bytes representations, and G2 is a bit bigger because it's an extension field, so it's twice as big at 96 bytes. GT is only used internally, so we don't really need to care about it, but it's a 12th extension of G1, so it's pretty big. It's 12 times as big as G1. And so, for example, the mainnet for drand is running with a public key on G1, so it means the public key is relatively short, and the signatures for each beacons are on G2. So the signatures are relatively big for the default mainnet chain. We can see it if we look, for example, at the /info endpoint on the HTTP relay. We can see the public key here. It's relatively short. It's 48 bytes. We can see also the period of the default beacon. So we can see here beacon ID and period. So period is 30 seconds, as I said. And the rest of the data is basically a way to identify the current set of nodes running with the group hash and the hash of the chain hash of the chain. So the value here named hash is a unique identifier for that network. So if we look now at a beacon on that network, so we've seen earlier when I was querying the HTTP endpoint /public/latest what it looked like. We had a round number, which is basically just the unsigned integer of size 64 bits of the current round. So we started in 2020 in August with the round 1. And since then, every 30 seconds, without missing a single beat, the League of Entropy has been producing rounds. And each round was incrementing basically that value. And each round is signed with a signature on G2, which is encoded as a compressed point. And it's in hexadecimal for reasons. And so it's taking twice as much space as the byte size of the point. So that would be 192 bytes. Now, the default chain It's operating in chain randomness mode. We'll see in a minute what that means. And that means we need the previous signature as well to verify the signature. Because usually what you signed with the different beacons is the round number. But here in chain mode, we also concatenate the previous signature to it, so that you cannot predict a future round without knowing the round before it. And that round, you can't predict it without knowing the round before it, and so on. So if you want to generate a future round, you will have to generate all the intermediate values for all the rounds in between. And then so the previous signature is just the signature of the previous beacon. So here we're at round 3,056,681. So the previous signature value is the signature of the round 3,056,680. And the most important thing, the thing we're producing, and we're basically telling people, hey, here it is, you can use it. Here is public verifiable randomness. It's the randomness field. And that is actually a hash of the signature. So the signature, it's a signature that is represented on G2, which is a group of an elliptic curve. It's an elliptic curve subgroup. And that means it has an algebraic structure. So it's not uniformly distributed on all the possible byte strings. So what we do is we take that, because it's still uniformly distributed amongst all the possible signatures by definition of a safe and secure signature scheme. And so we hash that signature to get a random value that is a byte string, a bit string. So here we can see the randomness. It's also in X, and it's taking 64 bytes. And that's because we're hashing it with SHA-256 and representing it in hexadecimal as well. Now, I mentioned there are two different modes for beacons. So the first one we've already seen is that chain mode, where each round is connected to the previous round, and basically you need the whole chain to verify a new round, and you need the whole chain to generate the next round as well. Now, in February 2022, no, wait, was it in May? I don't remember the date. Anyway, last year, we've launched an unchained mode on testnet, and that unchained mode is slightly different in the sense that the message that is getting signed by the group is not the hash of the current round and the previous signature. Instead, it's just the hash of the current round. So you can predict already round 3. We are going to be signing the message that is basically the hash of the value 3. So even if you don't know the previous signature, if you don't know the signature of round 2, you can still predict the next one. And why is that interesting? So as I said, the advantage of being in chain mode means you can't know in advance the future messages, and you also need to store all the previous ones to verify the next ones. So it's kind of stateful, and it's a bit similar to what blockchains are doing, right? But that being said, we're not a blockchain. Drand is not a blockchain because, we don't have transactions, obviously, but also what the only time where there is some sort of consensus happening is during the distributed key generation. Afterwards, once we've generated a secret key for the whole group, all the future values that are getting produced by signing messages are basically determined by that secret key generated during DKG. So it's not the same. And we don't need a consensus during the threshold signature generation. We just need enough partial signatures, and then we can combine them together into a group signature. So that's the chain randomness, right? It's kind of stateful because you need to know all the previous ones, and you also can't predict the future messages getting signed in advance because you would need all the previous rounds and your signature to do so. Now, the new unchained randomness mode is basically exactly what it looks like. It's unchained. So round 1 is the signature of the hash of 1. Round 2 is the signature of the hash of 2, and so on. And that is very interesting because it means anybody can predict the message that will be signing tomorrow or in 6 months, but we can't predict the signature. And that is interesting, for example, if we want to do time lock encryption or identity-based encryption using drand, because then you can use the message as a public key, and you can use the signature as a secret key, because the signature won't be produced by the legal entropy until the right time has come, right? So that's how we do, for example, to do time lock encryption, which is something we've been talking about on the blog, and we've also released the TLOC library in both in Go and JavaScript to do so. Also, it's quite interesting because verification is completely stateless. You just need to know the public key of the group and the round number and its signature, and then you can verify it. So I've been talking a lot about signatures, right? So maybe I should recall a bit what the BLS signatures look like. So we have a secret S, which is basically just an integer. We multiply a generator on, for example, here G1 with that secret, and we get a point P, the elliptic curve G1. At that point, P is really just S times G1. And in practice, what we're doing is that we have multiple shares for each node, and so there is a secret key for the whole group. That is the interpolation of all the shares of all the nodes, but it's not too important because the signature scheme behind the hood works really like in the same fashion for both the threshold or the regular 140 BLS signatures. So we have a public key P, which is a point on the curve, and a secret key S, which is just an integer. And then when we want to sign a message, what we do is basically we take the value M, the message that we want to sign, and we need to map it to the other group. So the group where we don't have yet, where we don't have a point yet. So here you can see I have P, which is S times M. So M is the message mapped on G2, and S is the same secret. So what I'm doing is I'm multiplying the message with the secret, and that's basically my signature. And when I want to verify a BLS signature, I can compute the pairing of G1 and the signature P, and that is equal to the pairing of G1 and the secret times the message. And because the pairing operation is bilinear, we can extract the value S out of it, and it's equal to S times the pairing of G1 and M, the message that is getting signed. And now, to verify it, I need to compare it with the pairing of the public key of the group, so PG, public key of the group, which is a point on G1, and the message. So that is equal to the pairing of the secret times G1 and the message. And again, by bilinearity, I can extract the secret S out of the pairing, and that is equal to the secret times the pairing of G1 and M. And so if everything checks out and the signature is a valid BLS signature, when you compare the pairing of G1 and the signature P with the pairing of the public key and the message, you should get the same value. And that is not leaking the secret key, because the secret key is really like inside, of it all. So it's hidden kind of in the pairing operation. The pairing operations allows us to extract the secret without knowing it. And so we can compare the two and see it's this. If it's here in the blue box, it's the same value, then the signature is correct. But here we can see, right, I have my signature on G2 and I have my public key on G1, but I could have the converse, right, and do the same operation with the generator of G2 and the message on G1, and it wouldn't change much. And so that's exactly what we did, what we launched in March. So we launched a new network, Fastnet we called it, which is using beacons on G1. And again, the beacons, the different beacons on G1 are exactly the same as on G2, except here we only gave a unchained mode, so we don't really need to care about the previous signature for the ones on G1, because we haven't launched a network in chain mode on G1, not yet at least. Nobody asked us about it, and it seems like users are happy with unchained randomness. So beacon on G1 would be just a round number, same size as on G2. The signature, this time it's much smaller. It's half the size of the signatures on G2. And the randomness, and again, the randomness is just the hash of the signature. So we could, we could not send it and people could compute it if they wanted to, or if you were doing something fancy with the public randomness if you need to do something fancy with the random beacons, you could also do your own derivation out of the signatures we're providing. The key ID being the signatures are unpredictable and uniformly distributed on the G1 group here. And so when you map it to a bit string using a hash, it's going to be uniformly distributed and unpredictable and unbiased as well. So as I mentioned, we have a second chain running on mainnet. So here we can see I'm accessing the second chain using its chain hash and the /info, for example, to see its public key. So here we can see, since it's on G1, the public key is much longer, and also it's the fastnet one. So as I mentioned, the period is much smaller at a 3-second mark. And the genesis time is March 1st because we just launched it in March. And actually, that network is going to be sunset this year because we identified a non-compliancy issue with our implementation of BLS signatures on G1, and we'll be launching later this month a new QuickNet network on mainnet that is RFC compliant with the for the signatures on G1. But that's a detail, and we just released a blog post about that if you want to check it out. So an interesting thing about drand rounds is that they map to a precise time because it's always the same period, right? So here we can see, I don't know, I round 4001 at 1 p.m. and 30 seconds. I can predict that the round 4010 will be at 1 p.m. and 5 minutes on the same day because it's every 30 seconds, for example, for the default network. And that's what we use for time lock. All right. And so that was the theory, right, that we need to kind of understand the beacons. And now we will look at the code. But I don't know if anybody had questions maybe first. No questions, I guess. So let me just go to the GitHub page of drand. So that's our GitHub, right? And we currently have 2 branches we're working on. There is the master branch, which is what's running in production, what's being released in releases. And we are planning to land a major revision of the code base in Q3 2023, so roughly maybe in September. And that is being developed on the develop branch. So the main difference being we've moved a lot of things into the internal folder to shrink the size of the public APIs we're exposing and so on. But it doesn't change much about the code. And so I'm going to demonstrate that with just the current, master branch, and the ID is the same. So we have a chain here folder with a beacon folder inside, and we can see quite a few things in there. And so these are the important things. So in the chain folder, we also have a beacon.go file, and that's the one defining the beacon struct. So the beacon struct is a previous signature, it's a round, and it's a signature, right? As we said. There are a few things to basically represent beacons in JSON and so on. And then if we look here, we have a function called randomness that operates on the different beacons. And that is pulling from the crypto randomness from signature function in the crypto scheme package, which is in the crypto folder here. So in the scheme.go, we have all the different schemes we've implemented for drand. So I was mentioning we have currently 2 different schemes running on mainnet. So one of them is the Pedersen BLS chain. So that means if we look here at the digest function we're using for signing and so on, that we will instantiate the SHA-256 hash function, and then we will first hash the previous signature before hashing the round of the beacon in Big Indian. And that will give us the digest that is being signed by the signature algorithm. Now, if we go down a bit, we can see we have other scheme, and most interestingly, we have here the G1, the Unchained on G11 that is running on Fastnet. And here we can see the digest function is much simpler. It's basically just the SHA-256 of the round in Big Indian. So much simpler because it's unchained. So we don't need to care about the previous signature to verify or to sign such a beacon. And now I mentioned we identify some issue with the RFC compliancy of the signatures on G1. And so we have a new signature, a new scheme, new drand scheme that is compliant with the RFC 9380 and the H2 curve RFC. And that is also in unchained mode for now. I mean, forever, actually, it's the unchained one. Anyway, going back to the beacons. So in the chain folder, in the beacon.go file, we can see we have a few public APIs here. So we have the string representation of a beacon that is basically only used for logging. So it's not really meant to be used in code. We have the get round function that is basically just the current round of the beacon. It's going to give you the int64 of the beacon. And we have the get signature that's going to return the signature, the get previous signature that's going to return the previous signature. So everything else is basically as you would expect for a drand beacon. The beacons are then stored in stores, but that is something we'll be discussing in another code walkthrough, because we have multiple stores and we also have multiple storage backends. Like you can see here, BoltDB, MemDB, so in-memory database, and Postgres SQL database as well. So we have multiple storage backends for beacons, but we'll be discussing it in a next walkthrough. So when you want to get a beacon, you're most likely to be using one of the clients here. So you can use, for example, the HTTP client, as we've seen earlier. And that is basically, something that is meant to be called in your code. And it allows you to construct a new client pointing to a HTTP endpoint. So you can use, whichever you want, and it works. We also have the gRPC client, which is sadly deprecated because different nodes used to be directly exposed to the internet. So anybody could talk to a node using gRPC instead of using HTTP. But yeah, that has been deprecated. The different nodes are now running in a closed network. So it's walled garden kind of, we got firewalls and everything to protect them. And so you can't talk gRPC directly to the nodes anymore. You have to go through the HTTP relays to talk to them. And the relays are actually also in the code for now, but we're working on extracting them. So if we go to the CMD file, we can see we have the gossip relay and the HTTP relay here with the code for the relay and everything. I don't know if there is anything else to be to say about the drand beacons. Yeah, so the most important things for the beacons is basically the scheme, the cryptographic schemes we're using to run. So the two that we're using are Pedersen BLS chained, which is using the previous signature in its signature algorithm, and the G1 unchained one, which is not. And we'll be launching a new network with the new scheme. So yeah, that's it. I guess that's about it for the code walkthrough. So I don't know if you had any questions or anything. So I'm afraid since the gRPC endpoints were deprecated, we can't really query directly the drand beacons using the drand command line. So actually, we could, but so let me start here. Let me start. Let me start a drand network locally. Oh, what's going on? Okay, one node. A second node. So we've seen last time in the code walkthrough with Patrick how to start nodes, right? So I'm not going to go through the entire process of creating a new network and everything. So here I have a network that I've created a while back. So it should start, and it should, you can see here it got an error sending the partial for round 8. So it should start to communicate with each other, and it should start to catch up. So I think that's what's happening here. Yeah. So the network has been catching up. It's still going here. Anyway, so here I have 3 local nodes running, okay? And so previously what you could have done with the gRPC endpoint would be to use the get value to get data from a remote node. But as I said, this is not possible anymore with the league network, because we're basically not using a gRPC endpoint. We're not exposing the gRPC endpoints anymore. So if we want to, for example, I don't know, get the chain info, and no, let's get the public data of the nodes running locally. I could do that by taking the group file. And that's one of the annoying things. To query the nodes, you needed to know the group files and everything. So here we can see I queried that group file and I got the round 7. If I query the group file for the other, because that was actually a test where I was deleting the network, so it's not really a good example. So that one worked better because I didn't delete the network, so I can get the round. And if I try again in a few seconds, it should be the next round because it's getting the latest one. Oh yeah, and the network is currently in catch-up mode, so it's going very fast. So it's basically generating new beacons as fast as it can. So it's going pretty quick. As we can see, we jumped almost 1,200 rounds. Anyway, so we can see here the round number, the randomness, and the small signature, and no previous signature. So that means this network here is actually in unchained mode on G1. And so I can also show you how to start the same nodes. So here, okay, that is how we start a node just to create a drand network. But now, what if we want to have a HTTP endpoint? So what we need to do is add a new argument to our command line here. And this is all, by the way, described in our documentation. So if you go to GitHub, go down, you should see here the installation and how to run drand locally, create a drand deployment, fetching public randomness. So that's what I was telling you. The gRPC endpoints are not working anymore, but you can use the HTTP endpoints and so on. And so here we have more documentation. And so if we look at the deployment, I guess, here, the deployment guide, okay, it's on our website, drand.love, in the operator doc. So here, the operator documentation, you have a deployment guide about how to do what. So it explains you how to start a drand daemon, which we've seen last 2 weeks ago with Patrick, with the TLS disable if you have a reverse proxy in front or whatnot. And here we can see one extra argument we haven't used yet. It's the public listen one. And here, that's what it says. If no public listen flag is provided, drand will not expose the public HTTP interface, which means if we want to expose a public HTTP interface, we need to provide the public listen argument to our node. So if I go back here, I can say public listen, I give it a local host address, and let's say, I don't know, 666, okay? I'm going to launch my node again. And now, if I query these endpoints, it should basically work just as described in the general documentation when we go to the public randomness. No, when we go to the, maybe it's in the operator doc as well. Yeah, here, public HTTP API. So if we go through the documentation and we try one of these, it must be in the developer doc. Okay, here it is, HTTP API reference. So that's the public endpoints we currently have. And if we go through these commands, well, not commands, HTTP APIs endpoints, we can see if it works or not. So let's try the chains one, okay? So I can say, okay, I will just curl, and then I will say /chains. And here we go. We can see our node responding saying, hey, I got one chain. And so now if we try with that chain /info, because that's the other public API we can see here, we should get some data about the chain hash, the chain that is running there, the network that is running. And that's exactly what we do. And that is not very nice, so we can see it nicer with G2. And we can see the public key here. We can see it's a BLS Unchained G1 RFC network, which was actually a development network. The name has changed. Now it's called RFC 9380. Anyway, and that's the default beacon. And so if it's the default beacon, we can actually skip the chain hash entirely. It's a special case for backward compatibility with the before drand was able to run multiple beacons at once, and we get the same info. Now, if I want to access the beacons themselves, I can do public /latest. I should get the latest round. Here it is. Now, the problem here is I haven't verified that beacon yet, right? So by using curl, I just get the data, okay? So if I want to verify the data, I have two options. I can use the Go library, and then I can use the HTTP client, which is verifying, which will verify all the signatures, or I can use the JavaScript client, well, not client, library again, which is an NPM and everything. And I think that should, yeah, that should bring us to GitHub. And there are a lot of examples, actually. If you look at the tests, like you can see here, the fastest known client test, HTTP client test, HTTP chain client test. I guess that's the good example. And that's basically what Patrick was showing us last week as well, when he was talking about the JavaScript clients. And this is going to verify the signatures. Now, if you want to do it yourself, verifying the signatures, what you need to do after you've queried it here is to parse it as a BLS 12381 point. And then you need also to parse the public key as a BLS 12381 point. And you need to go through the computations I've showed you here, here. You need to go through the whole verification. And that can be done easily using a BLS, for example, the BLS 12 Kyber implementation we have that allows you to work with Kyber points on G1 and G2, and you could do it by hand, or you could look at the Kyber test here. And if I'm not mistaken, at the end, here we got some examples of a test verifying a signature on G2. So we got the public key, we got the signature, we got the previous signature, which is actually, not a previous signature, but just a random string here, I think. It's the wrong one. So this is the Genesis seed. It's a special case. Anyway, and then you can instantiate the BLS suite. You can unmarshal the points into G1 and G2 points, and you can compute the pairings here and validate the pairing against the hash of the message and everything. So that's really like if you want to do it all by hand, but in practice, you probably don't want to do it all by hand, and you can rely on the JavaScript or on the Go libraries to do it. And I guess that's pretty much it on my side. So let me maybe stop sharing and see if anybody had any questions. Oh yeah, Patrick is saying in the comments, shout out to D, a cool CLI tool created by Thibaut from Cloudflare, because D is making it a bit easier to use the HTTP endpoints than the drand command line. Yeah, good point. Awesome. And I guess that's it. So I'm going to stop the recording.